These four videos demonstrate different degrees of autonomy for human-robot interaction for similar set of mobile and fixed-base robots for four different applications. The first video shows complete manual control, excluding different modalities of interaction. The second video compares augmented reality and mixed reality advanced driver assistance system with automatic lane detection but manual directional control. The third video explored mixed reality-based human-robot interface with autonomous navigation. Finally, the last video shows complete autonomous navigation in an airport taxiway.
Existing human-robot and collaborative robots involve a person operating with a single robot. However, with advent in drone and multi-agent collaboration technology, it is often possible and necessary for an operator to control multiple cyber-physical systems simultaneously. Where a person drives a ground vehicle and simultaneously undertakes a pick and drop task involving a desktop robot using eye gaze, gesture, or speech recognition-based interfaces. As it is seen in this video, the user uses eye gaze to control the desktop robot to pick the object and drop it on top of the ground vehicle. Next, the user is using touch to perform the same task, that is to pick the object by the desktop robot and drop it on top of the ground vehicle. So, for that the user is touching on the screen and based on that, it detects as click, and then based on that clicking event, the desktop robot performs the task. Next, the user uses gesture to do the same pick and drop task where the user moves his hand on top of the sensor, and based on that, the mouse cursor also moves on the monitor, and through that mouse cursor movement, the desktop robot also moves to pick up the object and drop it on top of the ground vehicle. After this, we will see the user is performing same pick and drop task via voice.
Charlie, Kilo, Delta, India.
After completing the pick and drop task, the user will again drive the vehicle to its starting point. It is seen that touch takes the lowest time and speech takes the longest time to complete the whole task. Whereas in terms of perceived cognitive load, eye gaze has the highest TLX score compared to others. It is also seen that there is no significance difference between touch and gesture-based modality and in between eye gaze and speech-based modality in task completion time. The future works will further investigate multiple combinations of UAV, UGV, and fixed-based robots for warehouse maintenance, object delivery, and agriculture-related applications.
In this work, we examine the effects of using extended reality interface for assisting drivers in takeover requests and in the first second of controlling the vehicle. We focus on developing a lane detection algorithm to keep the vehicles follow the ego lanes. We present a prototype of an augmented reality and mixed reality assistance system realized on a simulated environment. We conducted the user study to measure response time of participants in case of takeover request in autonomous vehicles. From statistical analysis, we observed that MR took significantly more time than AR in completing the task. We used mixed reality interface as AR does not provide depth perception. Although unfamiliarity and discomfort of physically wearing the HoloLens undermines its stereo vision effect, however, response time was not significantly different for both the modalities. Thank you.
This video, we are going to demonstrate virtual obstacle avoidance and heterogeneous multi-robot coordination in mixed reality with a human in the loop. This video demonstration consists of two components, virtual obstacle avoidance and heterogeneous multi-robot collaboration. We have a mixed reality interface which emulates warehouse type of scenario. There are virtual obstacles present in the scene as well as real obstacles. There are virtual buttons when pressed act as inputs to the robots. And when it comes to heterogeneous multi-robot collaboration, we have two kinds of robots, mobile robot and fixed based robot. When the user presses any button, both the robots have to coordinate in a way that the orange colored load is being picked and placed. The mixed reality interface emulates a warehouse kind of scenario augmented on the real world as 3D holograms. There are two fixed-based robots and hence there are two buttons that follow the user. Each button represents a command to the mobile robot to go towards a particular fixed base station. When the user pressed the button, the robot is going towards one fixed base station while avoiding the virtual obstacles present in the scene. It can be observed that these virtual obstacles are not present in the real footage in the top right corner. The robot is also observed to avoid the real obstacle in the scene while going towards the fixed based robot. The mobile robot uses ROS-based navigation architecture with A-star algorithm and dynamic window approach as global and local planners. As the mobile robot reached into the workspace of the fixed base station, the load which was carried need to be pick and placed. The load is detected by the camera mounted on the top of the fixed base robot and uses classical computer vision technique to determine its position in the scene. Thereby we achieve multi-robot collaboration in a mixed reality via a human in the loop. Thank you.
A report prepared by Boeing shows that the taxi phase ranks second in terms of risk of accident classified per flight phase. An automatic aircraft control system will help in reducing crew workload, thus reducing the risk of accidents and better surface traffic control. This paper addresses these problems and criteria by introducing a computer vision-based end-to-end autonomous taxiing system. This system includes lane detection followed by lane navigation algorithm to keep the aircraft over center line. It also helps in stopping the aircraft before entering the runway. The object detection and avoidance module is used to stop the aircraft to avoid collision with any kind of obstacles detected in line of the aircraft. The object detection module was compared with other state-of-the-art models and was found that it performed better than other. Later the model was fine-tuned with the proposed airport dataset for connecting to the proposed system. Finally, the overall performance of the system in different lighting conditions shows that the model can perform well in different lighting conditions. Thank you.